Hello, today we're going to take a very simple and basic introduction to Fermi-Dirac and Bose-Einstein statistics. And by way of comparison, we're going to compare them with the Maxwell-Boltzmann statistics or distributions. As far as physics is concerned, all basic particles come in two kinds, fermions and bosons. Fermions are things like electrons, neutrons, protons, and bosons are things like photons, or the famous Higgs boson. Now, as we shall see, Maxwell-Boltzmann statistics deal with molecules, or particles which are what are called distinguishable, and I'll explain what I mean by that in just a moment. Fermi-Dirac statistics deal with fermions, for example, electrons, and they are indistinguishable and they are subject to the Pauli exclusion principle. I will just review what both of those mean in a moment. Bose-Einstein statistics deal with bosons, for example, photons, which are also regarded as indistinguishable but do not obey the Pauli exclusion principle. And yes, before you ask, that is my washing machine making a row in the background. Now, what do I mean by distinguishable or indistinguishable? What we mean is, can two particles be identified as separate? Well, in the case of molecules, yes. You can see that one molecule is here, one molecule is there. But in the case of electrons, that's not the case. When we think about these things quantum mechanically, you'll recall that when we say we have an atom, which has a nucleus and an electron orbiting, we said that if you think of an electron as a particle, then you would expect it to spiral into the nucleus and for the whole thing to disintegrate in 10 to the minus 14 seconds. But that clearly doesn't happen. And the reason it doesn't happen is because quantum mechanically we don't think of an electron as a particle, we think of it as a wave. So here is a wave. Now suppose we take another electron. If the wave distribution is very close to the first, then we say that those two particles are indistinguishable because you cannot resolve the distance between them. And the basic rule of thumb is that the wavelength of the wave associated with the particle has to be very much less than the separation between the two particles. In the case of molecules, that's perfectly true. The molecular wave function has a very small wavelength compared with the distance between molecules on average. Whereas the wavelength for electrons and their separation is broadly comparable. So they are indistinguishable. Now, what do I mean by saying that electrons or fermions obey the Pauli exclusion principle but photons don't? Well, in my videos on atomic physics, you will see that the consequence of regarding electrons as having a wave nature as opposed to a particle nature is that they satisfy what's called the Schrödinger wave equation. And the Schrödinger wave equation has solutions which essentially say that the energy, if this is the energy, of an electron must occupy certain states, and it cannot occupy any states other than those. So there's the 1 state, the 2 state, the 3 state, the 4 state. In fact, there's an infinite number of states, but they are all discrete and separate. So no electron can hover in the gap between the two. It has to be in one of those states. And we also showed that the number of electrons that can occupy these states is governed by the Pauli exclusion principle. Essentially it says no two electrons can have the same 4 quantum numbers. So, for example, in the lowest state, you can have one electron spin up, one electron spin down. That is actually called the 1s state, and you can have 2 electrons in it. When you get to the n equals 2 energy level, you can have 1 electron spin up, 1 electron spin down in the s state. So this is the second energy level. It's the s state, and you can have 2 electrons in it. But you can also have 1, 2, 3 up and 1, 2, 3 down electrons in what is called the p orbital. So there's a total of 6 in that level, plus the 2 s electrons makes a total of 8 in that energy level. There's 2 in this one here. So essentially there are 2 states in the first energy level and 8 states in the second level. And here's the point. The Pauli exclusion principle says once those levels are full, if another electron comes along and wants to occupy an energy level, it cannot occupy level 1 because that's full. It cannot occupy level 2 because that's full. It has to go up into the next energy level. So even though electrons, like all of nature, want to occupy the lowest possible energy level, in fact they are constrained to occupy a higher energy level because all the spaces in the lower levels are already full. And that's what we mean by the Pauli exclusion principle. By contrast, if you are a photon and you don't obey the Pauli exclusion principle, then that means that all photons can occupy the lowest energy level, and you can have billions of them in that energy level. There is no constraint. The thing that separates bosons from fermions is that we say that fermions have a half integer spin, bosons have an integer spin. But that's a technicality. They are different. One of them is subject to Pauli, the other isn't. Now, to get us going, I think we'll start with the Maxwell-Boltzmann distribution because we can then compare the other two to it. So let's take this room full of air. So there's the room, and it's got air in it, which will be basically molecules of oxygen and molecules of nitrogen. And we know that those molecules will be moving around the room. Occasionally they will be bumping into one another. Occasionally they will be bumping into the walls of the room. And as they do so, they exchange both momentum and energy. And we know that each molecule will therefore have a velocity. When it hits another molecule, it may change that velocity, but for the time being, the energy of each molecule is given by a half mv squared. That's the kinetic energy, where v is the velocity. We can also say that whenever a molecule hits the wall and rebounds off of the wall, there will be a change in momentum, and we know that force is the rate of change of momentum. We also know that pressure is force over area. So the pressure on the walls of the room will be determined by the force, which is the rate of change of momentum as the molecules hit the wall, divided by the area of the walls of the room. So that's what actually constitutes the pressure of the gas. This is a gas here. The pressure of the gas on the walls, the ceiling and the floor of the room is governed by the fact that the molecules are every now and again hitting that wall, rebounding off of it. The change of momentum, or more importantly, the rate of change of momentum, determines the force on that wall. And if you divide that force by the area, you get the pressure. Now there is a pressure law, which I've covered again in one of my other videos, which says that if you keep the volume constant, then the pressure, this is the pressure, and we're plotting it against temperature. If you keep the volume constant, then the pressure is directly proportional to the temperature. As the temperature increases, so does the pressure, and as the temperature decreases, so does the pressure. So that essentially if you start in your room with a pressure and a temperature of this kind, as you reduce the temperature, the pressure falls, and it does so linearly. until some point here you will see that there is no pressure in the room at all. We're down to pressure equals 0. And this happens at a point which we call 0 degrees Kelvin, which is also minus 273 degrees Celsius or centigrade. And what does it mean if the pressure is 0? Well, if the pressure is 0, that means that the force must be 0. So the rate of change of momentum must be 0, which means that the molecules are not moving. The molecules have 0 velocity. That way they don't hit the walls. That way there is no change of momentum, no pressure. So at absolute 0, all the energy has, or at least all the kinetic energy, has been taken out of the molecules, and they all essentially are stationary. Now, if you were to plot the number of molecules in the room against their energy, so this is the number of molecules against the energy of each molecule, recognizing that some molecules will be moving fast, some molecules will be moving slow, so half mv squared, the kinetic energy of each molecule, will be different, you will find that there is a distribution. And the distribution looks something like this. And what that means is that there are some but not very many molecules which have a very low energy, some but not very many that have a very high energy. Most are in this region here, which is round about the average. And we showed that actually the average energy in the room, the average energy of all the molecules in a room is essentially the temperature. The temperature is just a measure of the average energy. And in fact, it's related in that the energy is equal to K times T, where K is Boltzmann's constant and T is the temperature. And Boltzmann's constant is very roughly 10 to the minus 23 joules per degree Kelvin, or very roughly 10 to the minus 4 electron volts per degree Kelvin. Now, if you increase the temperature of the room, you would expect the average energy, which is a measure of the temperature, to increase. And what you get is a distribution that looks like this as you increase the temperature. What happens is you get more molecules now at higher energy, and the average has moved up as well. But the area underneath the curves must be the same, because essentially the area under the curve is the total number of molecules in the room, and total number of molecules in the room is not going to change. On the other hand, if you cool the room, the distribution does this: it flattens out. Once again, the area under the curve will remain the same because it's the total number of molecules in the room. But essentially, as the temperature in the room increases, so this curve will flatten out more. At very high temperatures, it will look like that. And there will be far more molecules with higher energy at high temperatures than there are at very low temperatures. And of course, the implication is that if you go to 0 degrees Kelvin, then the curve will essentially look like this. All will have not necessarily 0 energy, because in quantum mechanics you don't always get 0 energy, but the lowest possible energy state that the molecules can occupy. They'll have no kinetic energy. They might have some internal energy. That's there, that's quantum mechanically there, but they have no kinetic energy. Now, if we take this coordinate here, which at the moment is the total number of molecules having a particular energy, if we divide that by the total number of molecules in the room, then these graphs remain the same, but now they show you the proportion of molecules having a particular energy. So a very small proportion have a low energy, a much higher proportion have that energy. And this is also, of course, a measure of the probability of the molecule having a particular energy. So if you take this curve here, it's highly probable that a molecule will have this energy. It's very much lower probability that it will have this energy. And so the idea of probabilities comes into the ideas. And that's what Maxwell-Boltzmann, Fermi-Dirac and Bose-Einstein statistics are basically all about. They are telling you what is the probability that any one of the molecules or fermions or bosons will have or will be occupying a particular energy state. Now the Maxwell-Boltzmann statistics, and I'm not going to derive these, it takes about 45 minutes to do these, and they're mathematics, it's mathematics not physics. But the probability, it's often written as F of E, that means the probability that a particular molecule, in this case because we're going to do Maxwell-Boltzmann at the moment, the probability that any molecule will have the energy state E, or will occupy energy state E, is given by 1 over E to the E over KT. So this is the exponential times E, that's the energy that we're talking about, divided by K, Boltzmann's constant, times T, the temperature. So that's the probability that an energy state will be occupied is given by this formula. And by way of illustration, what happens when T equals 0? In other words, when we're at absolute zero. Well, before I proceed, I better just deal with one issue which comes up in the comments on the YouTube channel from time to time. And that is my assertion that 1 over 0 is infinity, or 1 over infinity equals 0. And people point out that mathematically those are undefined. But what I think I can reasonably say is that if you say y is 1 over x, then it is certainly true that as x tends to 0, y will tend to infinity, and as x tends to infinity, y will tend to 0. In other words, as x gets smaller, y gets bigger. As x gets bigger, y gets smaller. We can all agree with that. And therefore, in the limit, we can say that 1 over 0 is infinity and 1 over infinity is 0 for the purposes of physics. And so, if in this formula here, t is 0, if we are at absolute 0, we get that the probability that an energy state will be filled is 1 over e to the e over kt. Well, t is 0, so kt is going to be 0, which of course is 1 over e to the infinity, because anything divided by 0, I've said, is infinity. E to the infinity is infinity, and 1 over infinity is 0. And so what you've shown is that there is no probability that any of the molecules will occupy energy states at absolute 0, because they will all be in the lowest possible energy state. And the graph of this equation here, it's simply a 1 over exponential graph. So it looks like this. Here is the probability of a molecule occupying an energy state, and this is the energy itself. And the graph is just an exponential, which shows that for a given temperature, there is a much higher probability that a lower energy state will be occupied than a higher energy state. But as the temperature goes up, the probabilities go up too, so that there's a much higher probability that a high energy state will be occupied at higher temperature than at lower temperature. So that's the probability that that energy state will be occupied at low temperature. This is the probability, much higher probability, that that energy state will be occupied at a higher temperature. Now we move on to Fermi-Dirac statistics. And I explained earlier in this video about Pauli's exclusion principle and how, for example, electrons occupy certain levels. So let's just take, by way of example, hydrogen. And a hydrogen atom has one electron in it. And in its ground state, that electron will be in the 1s level, and there'll only be one of them, so we call it 1s1. Now let's take another hydrogen atom, again with an electron in its ground state 1s1. What happens if we bring those two atoms together to form a hydrogen molecule? Well, Pauli's exclusion principle kicks in and says, hang on a minute, these two electrons appear to have the same four quantum numbers, they occupy exactly the same state, they're not allowed to do so. And so what actually happens is that the two states are very slightly pulled apart. One goes very slightly above the other. And then the two electrons occupy those states, but where do they go? Well, they will both try to get in the lowest possible energy level. And they can. As long as one is spin up and the other is spin down, they can both occupy this lower state. And the upper state is empty. And this gives rise to the idea that the lower state is called the valence band and the upper state is called the conduction band. I've dealt with this in the videos on atomic physics. But what happens if you take a substance like copper? Well, in a copper wire, for example, you will have billions and billions of electrons, billions and billions of atoms of copper. And all copper atoms have the first three energy levels full and one electron in the fourth energy level, which is a 4s1 electron. And every atom, and there are billions of them, so I can't draw them all, will have one electron in the fourth energy shell. So what happens when they all come together? This principle applies. All the energy levels have to be slightly different. And so what you end up with is essentially a band of levels which occupy of the order of 2 to 3 electron volts in separation. Let me move this up. A band of all these levels have to be slightly different, otherwise Pauli's exclusion principle would be violated. And then what happens is that the electrons start to fill those levels in the same way as we did up here by going to the lowest levels first. And so up, down, up, down, up, down, up, down, up, down, all the way up. But because each of these levels has got one electron in it when it has the capacity to hold two, you could in theory have another electron in here, a downspin electron. Since you don't, what will happen is when you fill from the bottom, you will fill to the halfway point. Everything below this will be full, everything above it will be empty. Just as up here, the lower one was full, the upper one was empty. And this is sometimes called the Fermi sea, and this is called the Fermi level. It is the highest level at which electrons occupy the energy level strictly at temperature T equals 0, and I'll show you why that is in a moment. But what we know is that an electron that is just below the Fermi level might be promoted into the upper band. This is called the conduction band, this is called the valence band. An electron that's hovering just a little below the Fermi level might be promoted up into the conduction band, and then if you put a battery across that wire, plus and minus, the electrons in the conduction band flow towards the positive terminal, and that's an electric current flowing, and that's how electricity flows. That's the quantum mechanical explanation of it. How do electrons get from just below the Fermi level into the higher band? Well, they absorb energy. Where do they get energy from? Well, possibly from the room temperature. Remember that we said that E equals kT, K is 10 to the minus 4 electron volts per degree Kelvin. So if you've got room temperature of, say, 300, which is about, what, 27 degrees Celsius, then you've got 10 to the minus 4 times 300, which equals 0.03 electron volts. Well, 0.03 electron volts, when you consider this whole band occupies 2 to 3 electron volts, 0.03 is not very much. But if an electron is very close to the EF level, the Fermi level, then it's got just enough energy, this 0.03 electron volts, just enough energy to push it up into the conduction band. Now, let's have a look at the actual statistics that govern all this. The probability that an energy state will be occupied, this is exactly the same principle as we had for Maxwell-Boltzmann, is in this case given by 1 over e to the E minus EF divided by KT plus 1, where E is the energy state that we're asking, is it occupied or not? EF is the Fermi level, the maximum level that is occupied when T is 0, divided by K, the Boltzmann constant, times T, the temperature, plus 1. Now, what happens when T equals 0? Well, if the energy level you're considering is greater than EF, in other words, if you're talking about energy levels in this area here, if E is greater than EF, then E minus EF will be positive. A positive term divided by KT where T is 0, a positive term divided by 0 will be infinity. And e to the infinity will be infinity. And infinity plus 1 will be infinity. So 1 divided by infinity is 0. And so the probability when temperature is 0, the probability of the energy levels above the Fermi level being occupied is 0. And that's exactly what we said. At the temperature T is 0, all the lower levels are full, all the upper levels are unoccupied. And there is no energy here to promote any electrons because T is 0. And therefore the energy available to promote electrons into the conduction band is 0. So when T is 0, these are all full, these are all empty, and there's no energy around to promote any electrons up. And that's why you get this solution here. The probability of an energy level above the Fermi level, which is what this means, being occupied is 0. Well, now let's keep T equals 0, but this time we're going to say what happens if the energy is less than the Fermi level. That means a level in this range here. Well, in that case, if we look at this formula, which tells us the probability, if E is less than EF, then E minus EF will be a negative term. And so that means that you effectively are talking about 1 over E to the E minus EF. You will still get an infinity term here, but essentially what you're looking at is Fe equals 1 over, this term is an e to the minus term, so it's essentially another 1 over e to the e minus ef. Now this term will become infinite because it's divided by kt, t is 0, so this becomes infinity. 1 over infinity is 0, so now we've got 1 over infinity, which is 0. But we must also remember that plus 1 term there. That should be a plus 1 term there. This is a plus 1 term here. And that gives us that the probability of the energy level being full is 1 over infinity, which is 0, plus 1, which is 1 over 1, which is 1. So the probability of the energy state which is less than the Fermi level being occupied is 1. And that's exactly what we said. When t equals 0, all of these energy levels below the Fermi level are full. All the energy levels above the Fermi level are empty. So if we plot the probability that an energy level will be occupied against that energy, and we'll say that this is 0.5 and this is 1, then what we say is let's make this the Fermi level here. What we say is that when t is 0, then there is 100% probability that all the energies below the Fermi level will be occupied, and there is a 0 probability that the energy levels above the Fermi level will be occupied. So we know that the Fermi level is occupied because that's the definition of the Fermi level. It is the highest level that is occupied when t is 0. So 100% chance, the probability is 1. That's 100% chance that the energy levels below will be full, and 100% chance that they will be empty, or in other words, a 0% chance that they will be full above the Fermi level. Now, what happens if we raise the temperature and apply it to our Fermi-Dirac equation? What you will get is a graph that looks a little bit like that. And if you raise the temperature a little more, you will get a graph that looks like that. What that is saying is that as the temperature increases, the closer you get to the Fermi level, there is a chance that, or put it another way, there is less than 100% chance that that energy level will be full. It's now only 90% or 80% likely to be full, and by contrast, there's a 10 or 20% chance that there is an energy level above the Fermi level that is occupied. And again, you can see why that is if I redraw all the energy states, and we said that that's the Fermi level, and that at t equals 0, everything below is full and everything above is empty. If you have an electron very close to the Fermi level and the temperature starts to rise, it may have enough energy to be promoted into the conduction band. This is the conduction band, this is the valence band. And that's exactly what this is showing, that when you get close to the Fermi level, it's possible that an electron will be moved or promoted from just below the level to just above, which means that there will be a vacancy here. So the probability is not 100% that the electron will be here, because it might be here. But of course, it's still 100% likely that the electrons will be occupied in the lower levels, because at lower levels, an electron down here, if all it's going to get from, let's suppose that T equals 1. Well, if T equals 1 degree Kelvin, then the energy available to the electrons will be kT, which is 10 to the minus 4 electron volts. Well, we said that this gap here is something like 2 to 3 electron volts. If all you've got available to you is 10 to the minus 4 electron volts and you're sitting right down here, you can't jump all the way up there. You haven't got enough energy. And you can't jump to the next available energy level because that's already full. And Pauli says, sorry, keep out, we're full, there's no more room. So electrons down at the very lower levels cannot move because they don't have enough energy. And that's why, as the temperature increases, there will still be a probability of 100%, probability equals 1, that the that the energy levels at the lower level down here will continue to be full, because there's only enough energy to promote the electrons that are very close to the Fermi level into the conduction band. But as the temperature increases, so there is scope for electrons lower down in the band to be promoted, so that if temperature gets up enough, you might get something like this, where now an electron quite low down in the band that's the new curve, an electron quite low down in the band has got enough energy to get up into the conduction band. And now let's look and ask what happens if the temperature is greater than 0, but you're asking what happens if the energy level we're concerned about is the Fermi level. Well then the Fermi-Dirac statistics formula becomes 1 over e to the e minus ef over kT plus 1. Whoops. That's e to the e minus kf over kt plus 1. That was the formula. That's the Fermi-Dirac formula. And that, of course, becomes 1 over e to the, well, if e equals ef, then e minus ef is 0. So it becomes 0 over kt plus 1. And e to the 0 over kt, well, e to the 0 is 1. So this becomes 1 over 1 plus 1, which is a half. Oh. So what we're showing there is that when the temperature is greater than 0, the probability that the Fermi level itself will be occupied is exactly 1/2, which is why when I drew this chart up here, I made sure that no matter what the curve does, at the Fermi level, it always has a value of a half. So effectively these lines become symmetric. As the temperature goes up, you might get something that looks like this. But at the Fermi level, the probability will always be 1/2. And finally, let's consider Bose-Einstein statistics. And the formula associated with the Bose-Einstein statistics is actually very similar to Maxwell-Boltzmann and Fermi-Dirac. It's that Fe, the probability that the state E is full, is e to the e over kt minus 1. And that minus 1 simply reflects the fact you can derive these equations. As I say, it takes about 45 minutes in each case from just basic statistics theory. But what that minus 1 does is to tell you that the bosons, if we're considering, for example, photons, are not subject to Pauli's exclusion principle. So just to remind you that whereas with the Pauli exclusion principle, you got a band and those bands would be occupied up to the Fermi level, that's electrons or fermions. When it comes to bosons, they can all occupy the lowest energy state, and there can be billions of them. An unlimited number can all occupy the lowest state. Now, they don't all occupy the lowest state because if there is temperature, if there is energy, then those photons can be promoted to much higher states. But the question is, if you take bosons, photons, down to T equals 0, what happens? The answer is they all condense into a single state. And that is actually called a condensate. So when you hear the term the Bose-Einstein condensate, what that really means is that in relation to bosons, when the temperature is 0, they all condense into a single lowest possible energy state. Now, Bose and Einstein predicted this condensate in 1925. It wasn't actually achieved until 1995, when using rubidium atoms, a temperature of about 1 billionth of a degree Kelvin was achieved, and the bosons were observed to go into a condensate. And that work was done by Cornell, Wieman and Kettle, for which they won the Nobel Prize in 2001. Well, that is a very simple, basic overview of the Maxwell-Boltzmann, the Fermi-Dirac and the Bose-Einstein statistics. So you have a rough idea of what they are and what they're used for. In each case, they tell you the probability that the particle that you're looking at, whether it be a molecule, a fermion like an electron, or a boson like a photon, is occupying a particular energy level.